So I gave a little preview of what I was going to talk about when I gave the opening remarks today, just talking about um, Espresso and what Espresso is building as really a marketplace for shared sequencing. Another way of describing this is calling it ad hoc shared sequencing. The idea that it's not that you're taking these rollups which have their centralized sequencers today and imposing on them another external sequencer or sequencing protocol that they give up their rights to sequencing to. Rather, it's about ad hoc shared sequencing is where they can sequence for themselves, maybe most of the time, and when the opportunity arises to sell their sequencing rights to third parties who value those sequencing rights more and are willing to pay a premium for them, then that transaction, that sale can occur. And this is even compatible with this idea that you may have heard of based rollups or based sequencing. And it's a result of the evolution of this idea. If you haven't heard of it, then you'll learn about what it is in this talk. But it's the most Ethereum aligned way of doing sequencing. So without delay, let's talk about what this is all about. So first of all, I've already said this in earlier talks. You probably come in here already knowing this, but maybe not. So what are rollups doing really? Rollups are horizontally scaling Ethereum. Right? Ethereum as a base layer that's scaling bottlenecks. Rollups enable the application layer to add its own servers, execute transactions outside of the Ethereum mainnet, and prove what happened to the Ethereum mainnet. Every application can even do this on its own, or you can have super applications like Arbitrum, zkSync, Optimism, Polygon, etc. that host many other applications on top of them. So you can have virtual machines. You can have a diversity of virtual machines that work differently from the EVM. They don't have to be the EVM. They could be an SVM. Eclipse is building an SVM, the Solana virtual machine on Ethereum. But the main point is that it allows for this sharding of computation across applications. If you add an application, you can add your own servers that execute for that application, and you don't burden the validators of Ethereum with your additional transactions. It's a very powerful concept. It also allows powerful nodes to help weaker nodes verify state, taking advantage of this natural heterogeneity that already exists in networks. Okay, so this is great, but today rollups run isolated, what we call sequencers. And what does that mean? Well, it means that they're processing their own transactions completely independent from one another, and it inhibits the ability of an application on one rollup to interact with an application on a different rollup, which arguably removes one of the main value propositions of Ethereum to begin with, that differentiates it from Web 2, which is that if you and I build an application, we don't have to do a custom integration with each other. They can just immediately talk to each other. Right? Users can access some decentralized exchange in order to trade an asset that I made and deposit it into my lending protocol, and then give it to you, and then buy an NFT in your protocol. And we didn't have to do any level of coordination. We just deployed to Ethereum. That's what makes Ethereum so valuable. And this is destroyed to some degree by the layer 2 because there isn't just one layer 2, but there's many layer 2s. Right? So yes, you can build your own app chain, but you risk being isolated from all other applications. It also results in liquidity fragmentation. And the value of Ethereum, as you've heard me saying, is in its unity, not fragmentation. Seamless interoperability of applications is the promise of trust, minimized infrastructure, and what differentiates Web 3 from Web 2. So let's talk about what is the role of this sequencer. Well, the sequencer is collecting these transactions. If it's a ZK rollup, it's summarizing them and posting a proof to Ethereum. If it's an optimistic rollup, it just posts the summary and allows for a challenge window where somebody could challenge the summary. But what it's really doing, the power of the sequencer, besides all of this rollup specific stuff, is that it gets to determine the next block for the rollup. It gets to determine which transactions are included in the rollup and their order. It may even run an auction among builders who may have a better way or better knowledge of how to best construct that block. So you can think of the power of the sequencer as having the power to run this auction among builders for the right to produce its next block. This is the same dynamic that happens in Ethereum today with leaders or proposers within Ethereum's consensus protocol, which auction off block building to providers like Flashbots. Now, base sequencing is actually the original concept of a rollup. The original Arbitrum white paper didn't have a sequencer. L2 nodes would just read the finalized transaction list from the L1. Transactions would be stuck directly into the smart contract on Ethereum, and then L2 nodes would just read from this, execute the transactions. Ethereum wouldn't execute them. It would execute them and then report what happened to Ethereum, right? Which gives the layer 1 the ability to actually do the sequencing, not only for your rollup, but it's also doing it for all other rollups at the same time. The advantage of this is that it inherits the decentralization and liveness and censorship resistance of the L1, but even more importantly, it results in improved interoperability, not only between rollups, but also between rollups and L1 applications. This second point was not appreciated in the original design of rollups. We didn't really talk about how base sequencing, which was the original design, has this additional interoperability benefit. It's only more recently that we've come to appreciate what that is. And I'll talk about that a little bit more. I just want to say that why is this so important? Well, ultimately, users don't care which ecosystem they're on. They just want a secure, convenient, and low-cost experience. And which way or another, they're going to try to satisfy their intents in the most efficient way possible. So this will be most efficient for applications that are deployed to rollups with the greatest unity, with the greatest interoperability, not only with each other, but also with smart contracts on the Ethereum L1. So why does base sequencing help with interoperability? Okay, well, let's consider an example. It's a simple example of an arbitrage opportunity between two automated exchanges on different rollups. Okay, if there's some common proposer, and this would happen if the rollups were using the layer 1 smart contract to do their sequencing. What it means is that the layer 1 proposer, the node that's elected to propose the next Ethereum block, is also proposing the next blocks of these two different rollups. So let's call this the elected L1 proposer. If a user wants to take advantage of arbitrage between an AMM on rollup A and an AMM on rollup B, an automated market maker, it says I want my transactions on rollups A and B to execute atomically, then this elected L1 proposer can promise that it will do that to the user, maybe in exchange for a tip. It says, I promise your transactions will execute atomically, and if it doesn't, then here is some huge amount of collateral that I'm putting up that I'm going to get slashed for if I violate this promise. So violating a promise is a slashable offense, and the user maybe even could collect damages from that escrow contract, so it can function like an insurance policy. Right? So this elected proposer has the full power to do this without any risk because it has the autonomy over the next updates to both rollups. This would not be the case if the two rollups weren't sharing a proposer. If each of them had their own centralized sequencer, then you could maybe have a builder that says, oh, I'm going to try to fill your promise, but this builder would take on a lot of risks because it might send the transaction to the rollup A sequencer, the other transaction to the rollup B sequencer, and the rollup A sequencer might include the transaction while the rollup B sequencer drops it. So it could try to make this promise, but it would take on a lot of risk, and so if it wants to offer insurance, it's going to have a much more costly insurance policy, right? So it's all about reduced risk. Sharing a proposer reduces risk, which ultimately reduces the cost for users. These promises are also known as pre-confirmations. So a shared proposal for a bundle of multiple rollups can act as a liquidity provider. It can make promises to satisfy user intent, such as atomic execution of several transactions across different rollups, even conditioned on the joint state, like conditioned on the price of an asset on some Uniswap oracle on Ethereum. It can also provide very fast confirmations within less than a second of what it has proposed. And if you trust it and you trust the collateral that it has staked beyond its promise, then you can get extremely, extremely fast finality for your transaction. It can also coordinate message passing between what I call zero-knowledge provable chains. So chains that have implemented a ZK rollup, but in fact, every chain is ZK provable today because we have general-purpose zero-knowledge virtual machines. So as the zero-knowledge technology is maturing, even optimistic rollups could be proven with zero knowledge. So this is something that Polygon Ag Layer has also written about, and it's a very, very elegant design. But basically, if you coordinate the simultaneous construction of two different blocks across two different rollups, then as I'm constructing these two different rollup blocks, I could do a transaction in one that passes a message to the other chain. I pass the message to the other chain along with a proof that the message is correct. The other chain processes that message, does something, passes a message back to the other chain, and so on and so forth. And what's actually really cool is that I could pass these messages and construct these proofs at a delay, and only at the very end aggregate all these proofs that I'm constructing. That's Polygon Ag Layer. So if that was confusing, don't worry, it doesn't really matter. The main takeaway point is that with ZK technology, we can achieve synchronous interactions between different L2s and even between L1 and L2 contracts facilitated by a common coordinator, i.e. a shared proposer who has the right to produce those rollup blocks at the same time. Again, violating a promise is a slashable offense. Users could collect damages for violations of promises, which turns pre-confirmations into a form of insurance. There are many examples of cross-domain user intents, capturing arbitrage. I've talked about just finding the cheapest way to execute some swap, which may be multi-chain involved. Making sure that, like, let's say I want to buy an NFT on one chain, but it requires me to acquire a certain asset to do that. I don't have that asset. My cash is on Arbitrum, the NFT is on Zora and Optimism. I don't want to bridge my assets, then do some kind of swap, and only to then fail to buy the NFT because somebody else bought it first. Right? So an example of a cross-domain intent would say, I only want all of this to go through if it actually succeeds in the end, across all these different chains. So this sounds wonderful. Okay, but what is base sequencing missing? Why were external sequencers introduced in the first place? Two main reasons. One, better data compression. Okay, an external sequencer collects transactions over time and can optimize when it posts them to the Ethereum L1. It doesn't have to post it in every single Ethereum block, and if you wait longer, collect more transactions, you can compress the data, and that gives you a lower data availability cost. The second reason is fast, low-risk pre-confirmations. So, yes, you can make these promises. You could promise that you could promise to a user that you included some transaction in the L1 block that promise takes only 100 milliseconds to verify, but you still take on some risk because there's a risk that Ethereum will reorg. In fact, until 15 minutes have elapsed, there's still a chance that Ethereum transactions will reverse. But an external sequencer can pre-confirm pure L2 transactions that don't depend on unfinalized L1 transactions, and it can do this with no risk because it doesn't matter which way Ethereum forks. This external sequencer, if you have an external sequencer, will ensure that any fork of Ethereum will include these transactions. Okay, so these vast, very low-risk pre-confirmations are the second major reason why external sequencers were introduced. Now, is there a middle ground? Yes, there is a middle ground. What you can do is you can still have base sequencing, which is really about allowing the layer 1 proposer to also be the proposer for the layer 2. But you also introduce what we call a fast finality gadget on top of the layer 1, where L1 validators can actually opt in to participate, and you could have a tremendous amount of staked ETH collateral here, perhaps assisted by EigenLayer. And this fast finality gadget is reaching finality much faster than Ethereum, even within a few seconds. What happens here is the L1 proposer from the layer 1 is now collecting the transactions. It's producing the super block for both the rollups and the layer 1. But what it's additionally doing is it's getting the approval of this fast finality gadget. So a rollup smart contract on the layer 1 will require transactions to be first confirmed by this fast finality gadget, which is a BFT consensus protocol. And this allows simultaneously, number one, still L1 composability because you have a shared proposer with the L1 who's building the L1 and L2 blocks together. But because of this notarization from the fast finality gadget, you get what I call conditional finality. So the finality of any pure L2 transaction is conditioned on the finality of the most recent L1 block it depends on. And for some L2 transactions, that may be very, very final, right? It may not be affected by the most recent transactions on the L1. They're just peer-to-peer trades, for example, wouldn't be. and those can be instantaneously final. So you get, in some sense, the best of both worlds in this design. But there's one more thing. So there is still a finality versus composability trade-off of being a base rollup, because maybe for peer-to-peer trades, there isn't so much dependence on the state of the Ethereum L1, but anything that involves maybe like a trade in Uniswap is going to depend on the state of the Ethereum L1. So base rollups with a shared finality gadget still have only conditional finality, whereas non-base rollups get they don't have synchronous interactions with the L1. They only have asynchronous interactions, but they get this unconditional finality. And this unconditional finality is something that's very, very powerful. So I want to do a quick demo demonstrating the benefit of shared finality for non-base rollups. I'm going to demonstrate how this reduces the risk of bridge transfers. It's going to make them faster and lower cost. We partnered with Across, which is a bridge, to demonstrate 7-second bridging between Arbitrum Nova chains, which are sharing the Espresso system as a finality gadget. So quickly, how Across works, well, it's a bridge where users deposit funds into a liquidity provider contract on one rollup, and this liquidity provider also has funds on a second rollup, rollup B. Now, normally it's very risky to release the funds on rollup B before Ethereum L1 finality kicks in, and that could be 15 plus minutes. Maybe even longer if you want to wait for the fraud-proof window for, like, say, Arbitrum to expire. But relayers participate in the Across network, and they see the deposit, and they're willing to take on some risk. So they compete for the opportunity to fill the bridge transaction. The relayer takes on the risk by releasing funds to the user on rollup B quickly, and it will get refunded by the liquidity provider once the deposit transaction file is on rollup A, which typically on Across takes a couple hours. Normally, these relayers still face this steep risk speed curve. Bridging is either slow or high cost. A latency of a few minutes on Across costs around 4 basis points between major rollups. But when rollups are sharing the Espresso finality gadget, this lowers the risk, and it enables bridging to take seconds at close to zero cost because they don't take on risk. So I'm going to demo here quickly. This is just a video for sake of convenience. But what we're showing here is we spun up 2 Arbitrum Nova chains on the Espresso system. They're sharing Espresso as a finality gadget. And what you're seeing here is that we made an Across bridge transaction, and it got finality from Espresso within just 2 seconds, even though it's going between 2 different Arbitrum chains. And the Across relayer was able to fill the transaction after only 7 seconds. Right? So we had 2 seconds to wait for finality from the Espresso finality gadget, and then an additional 7 seconds that the Across bridge took to provide the funds to this user on the second chain. So a user was able to bridge transactions from Arbitrum chain 1 to Arbitrum chain 2 at very low risk to the relayer and at very low latency, less than 10 seconds to the user. So how am I running on time, Ian? 5 minutes. Okay. So I want to close with one more thing, which is coming back to this marketplace, right? So what else is based, or what I would call vanilla shared sequencing missing, especially given the status quo of rollup sequencers today, right? MEV capture for rollups. I talked about chain sovereignty as a big theme in my opening talk at the beginning, if you were here. And one of the things that rollups have introduced, in addition to scalability, is chain sovereignty for applications. Right? Applications now have access to a revenue stream that they did not have access to before. And giving that back, to a shared sequencer or to the L1 would be a huge ask. It's just not going to happen. And so, because enshrined rollup sequencers have this additional revenue, we need to figure out a way to enable synchronous composability, better interoperability, all the advantages of base sequencing that I talked about, but while allowing these sovereign chains to still have this additional revenue capture. And there is a solution. What we need is a mechanism to redistribute sequencing MEV to rollups. So what comes from this is what I call a shared sequencing auction. And I'll talk about at the end why you can just reimagine this as a shared sequencing marketplace where the rollups are participating and effectively selling their block space two sequencers, some of which they could operate, some of which other people could operate, who are bidding for the right to propose for multiple rollups across the ecosystem simultaneously. So we have an auction where basically proposers would be competing to produce a superblock for multiple rollups that would then get finalized by this shared finality gadget. What does a shared versus isolated auction look like? Well, remember, when rollups run their own sequencers, they also run auctions. They run auctions among builders, but they're each running their own auction separately. Right? So nobody is able to bid on the ability to produce a block for two different rollups at the same time. And I may be willing to bid nothing to produce optimism on its own, nothing to produce arbitrum on its own, but a tremendous amount to produce them both at the same time, because that allows me to satisfy some cross-domain user intent or take advantage of arbitrage or something like that. So this shared auction is creating a surplus value, right? Bids may be higher on the combined block space than on individual, but how do we share this with rollups? Is there a stable mechanism through which rollups can dynamically participate and be convinced that they're better off than running in isolation? So the solution is called a combinatorial auction. We allow proposers to bid on any combination of rollup bundles. Each bid is for the right to propose this bundle of blocks in a specific slot. And for each slot, what we do is we would select the partition of rollups into bundles that maximizes this auction revenue. I'm going to ignore the inefficiencies of combinatorial auctions, which is exponential, and it's a detail that I'll talk about later, but this is the simplest way to present this idea now. Believe me, that if you want to talk to me about that, we can talk after. There's definitely ways to mitigate that exponential complexity. So what happens at the end of this combinatorial auction is we distribute to every single rollup at least its highest bid. Okay, so every rollup can also bid on itself, which functions as a reserve price. If a rollup bids too high on itself, it may exclude itself from bundles and just sequence itself on its own, but at least it doesn't screw it up for everyone else. We also would burn part of the bid, which can further disincentivize what I call shill bidding, is where you bid too high on yourself, and this functions like what's called a harbinger tax. So how is this base sequencing? Like, what about the L1 proposer? I thought the L1 proposer is supposed to be involved for this to be base sequencing. Well, after running this combinatorial auction, the L1 proposer for the Ethereum L1 block has the option to purchase proposal rights for any bundle that was produced through this auction at the winning bid price, maybe plus a premium. Right? And this always exceeds the sum of the reserve prices for rollups within that bundle. So effectively, we're just giving the L1 proposer an elevated status within this marketplace. It participates as one of the sequencers, but for achieving this maximum alignment with Ethereum, and for trying to optimize the efficiency in the system, we always give it the right of first refusal. It can always buy the ending result of the auction from other sequencers who have won that. Not all L1 proposers may participate in this, so sometimes they may not come in and buy it, but sometimes they will. So what is shared based sequencing after all, whether it's based or not? It's really a marketplace through which rollups sell block space to shared proposers who create surplus value by satisfying user intents across multiple chains, right? And which for base rollups includes the Ethereum L1 chain itself. And that marketplace is what we are building at Espresso. So thank you. If you are curious to follow our progress or hear more, follow us on Twitter. Feel free to reach out, and thank you for coming to our event today.